Hello students, in lecture 10 of your course Advanced Calculus, here we discuss the properties of Jacobian, certain examples related to these properties, and one exercise is given for your practice. So let us see the properties of Jacobians. So mainly we have three properties here. If u and v are the functions of x and y, then del uv del xy multiply del xy del uv is equal to 1. So this is the first property. Then second, if u and v are the functions of r and s, where these r and s are further the functions of x and y, then you can find the Jacobian of the transformation from the variables uv to the variables xy, and it can be obtained like this: del, because here you can see that u and v, these both are functions of r and s, then these r and s are further functions of x and y, and we want to find the Jacobian of this transformation, the direct transformation from uv variables to xy. So that is why here we are finding del uv by del xy, that will be equal to the Jacobian of uv for the transformation uv to rs, then the Jacobian of the transformation uh, from rs to the variables uv. So that is how you can find the Jacobian of this type of transformation. Again, if you the third property is there, if the functions u, v, w of independent variables x, y, and z are not independent, or the same thing we can write the dependent or related, then the Jacobian of u, v, w for the transformation, the Jacobian of the transformation from variables u, v, w to x, y, z, that is del u, v, w by del x, y, z is equal to 0. So from here what you conclude that for some transformation, suppose you are having the variables u, v, w, and these are the functions of x, y, and z, means this is the transformation from u, v, w to x, y, z. If in this situation this Jacobian comes out to be 0, then you say that these u, v, w are dependent, or you can say they are related. That means there must be a relationship among these three variables or these three functions, you can say. So whenever you have the value of Jacobian equal to 0, then you can say that these u, v, w are dependent, or you can say these are related. That means there must exist some relationship, maybe u, v plus w equal to 0, or maybe u square plus v square by w square equal to something. So that way you can say some sort of relationship will be there. So this was the third property. Now if we for these properties we see the examples with respect for corresponding to all of these properties. So for property 1 we have example 1 here. Yeah, this is example 1. If x is equal to uv, x is equal to uv, and y equal to u plus v by u minus v, then find del uv over del xy. If you look at the situation, here, you can see that x is given to be a function of u and v, and y is again given to be a function of the variables u and v. In fact, what is happening here, you are given the transformation from the variables x and y from the variables x and y to the variables u and v. But you are asked to find the reverse thing, the Jacobian of the transformation uv to xy, uv to xy. So how to find this Jacobian? In fact, there are two ways. Either first from these two relations x equal to uv and y equal to u plus v divided by u minus v, either from these two relations you find value of u in terms of xy and value of v in terms of xy, and then you know the direct formula of Jacobian, del uv over del xy. But if in the situations when such kind of explicit expression is difficult to obtain, then in those situations we can apply the first property that gives you, what is the first property? Just look at the situation again. In the first property, you know, you are given that the product of this del uv over del xy multiply del xy or del uv is 1. Means if you find the value of this, the value of this will automatically be obtained by taking the reciprocal of that. So the same idea we are going to apply in this example 1. So see here what we are doing, we are not obtaining the explicit expression of u in terms of x and y, nor the expression of v in terms of x and y, but what we are going to do, we are going to apply the property 1. So here obviously from this expression it is easy to find del x over del u, del x over del v, and similarly from this expression it is easy to obtain the values del y over del u and del y over del v. So we can find del x over del u, del x over del v, del y over del u, del y over del v. Okay, so here we can obtain the value of del xy over del uv like this: del x del u, del x del v, del y del u, and del y del v. So from here you can see del x over del u is equal to v, so that is there. Then del x over del v is equal to u. Then del y over del u, you differentiate this partially with respect to u, you obtain this expression. Similarly, when you differentiate this with respect to v, we obtain this expression. So in this way, this del xy divided by del uv gives you this determinant. Now you have to simplify this determinant. What we can do here from the first column, you can see v is common, so we take v outside here. Then from the second column, you can see u is common, so you can take u outside. Further, if you look at the row now, then in the row 1 upon u minus v square is common, so that can be taken outside. Then what we are left with here, it will be 1, and here it is minus 2, then here 1 and it is 2. Okay, then you simplify the determinant. 2 1s are 2 minus minus of 2, so that it becomes 2 plus 2, that is 4uv over u minus v square. But now this was not your uh, aim to find out the value of del x over del y, but you wanted to find out the value of del uv over del xy. But from the property 1, you know that del uv over del xy multiply del xy over del uv is equal to 1. This is from the property 1. And you have obtained the value of this one. And the value of this is 4uv over u minus v square. You are substituting it over here, and this is equal to 1. Then what do? You take this on the right hand side. In fact, you get the value of del uv over del xy is equal to u minus v square divided by 4uv. So this gives you the desired answer, the value of del uv over del xy. So this is example 1 regarding property 1. Now I'm going back to the property 2, what it says. Property 2 is basically the chain rule. when you are given that u, v are functions of r and s are further functions of x and y, in that case the value of del uv over del xy can be obtained like this in the second property. So let's do the next example here. Example number 2. Find the value of Jacobian del uv over del r theta. So what is given? Here you are given that u, this u is a function of x and y, v is a function of x and y, and further the function x is function of r theta and y is function of r theta. So obviously you can see here transformation is like that. From uv to we are transforming the variables uv in terms of x and y here, so uv to xy in fact. Then xy's are further given in terms of two variables r and theta. So you want to find the Jacobian of this transformation uv to r theta. So definitely the Jacobian will be like this, del uv by del r theta. But how to find the value of this? For that you have to obtain the Jacobian of this transformation first, means del uv over del xy, and then you will obtain the Jacobian of this transformation, that means del xy to del r theta. And then by applying the second property of the Jacobian, we can simplify this problem. So you see, first we find here del uv over del xy, del uv over del xy. Obviously, the value is del u over del x, del u over del y. Then del v over del x, del v over del y. So from this expression, I can have del u over del x, that is equal to 2x, and del u over del y gives you minus 2y. Similarly, del v over del x gives you 2y, and del v over del y gives you 2x. So after simplification, you can have this value is equal to 4 into x square y square. But from here you can see x square plus y square can give you r square. So the value of del uv by del xy is equal to 4r square. Second thing you are going to obtain, as I explained earlier, now you will obtain del xy over del r theta, means del xy over del r theta. The value can be given by this formula here, determinant of del x del r del x del theta, del y del r del y del theta. You obtain the values of del x by del r from this. Del x by del r is cos theta, del x by del theta is minus r sin theta. Similarly from here, del y over del r is sin theta, and del y over del theta is r cos theta. So you substitute the values over here and you simplify this determinant, it gives you r. Now come to the your target. We wanted to obtain the value of the Jacobian del u v divided by del r theta. So that will be using the property second of Jacobian. This will be equal to del uv over del xy, then del xy over del r theta. This we have obtained is 4r square, and obviously this was r here, so the value comes out to be 4r cube. So here we have applied second property of the Jacobian. Now next we move on to the third one. The third property was regarding the functional dependence of variables. So you just go back to the third property. If we have the function u, v, w of three independent variables x, y, and z, and if we obtain the value of this Jacobian del u, v, w divided by del x, y equal to 0, then these variables u, v, w will be dependent or functionally related, means there will be some sort of expression which will connect these three variables u, v, and w. So let us visualize the situation or demonstrate the situation with the help of example 3. So here you can see, verify whether the following functions are functionally dependent. So according to property 3, you know that the variables will be functionally dependent if the respective Jacobian comes out to be 0. So the values of u and v are given over here. U is equal to x plus y divided by x minus y, and v equal to tan inverse x plus tan inverse y. So in fact here we have only two functions or the variables u and v. In terms of another two variables u and v are transformed using the values x and y. So this is the transformation from uv to xy. So you can see for this kind of the Jacobian, we need to find del uv divided by del xy, and these will be functionally dependent if we find the value, that if the value of this comes out to be 0. For the three variables, we have seen that u, v, w, in fact the property has been written for the three variable, but it is true for two variables, maybe four variable, five variable. So it is true in general. So for two variables, I can say that u and v will be functionally dependent if this Jacobian comes out to be 0. So let us check. Here del uv divided by del xy is equal to del u over del x, del u over del y, del v over del x, del v over del y. This is the definition by definition of the Jacobian. Now let us find the value of del u by del x. Del u by del x can be obtained from this expression. Differentiate this partially with respect to x. So you get the value it comes out to be this. And again differentiate u with respect to y. You will see the value comes out to be this one. Then del v over del x is equal to, means we are partially differentiating with respect to x, that means this part will be 0, differentiation of this part will be 0, and the differentiation or derivative of this part with respect to x comes out to be 1 upon 1 plus x square. Similarly for del v over del y, we obtain this value. Now we simplify this. So after simplification, you can see that the value comes out to be 0, this minus this. So when the Jacobian, the value of Jacobian is 0, therefore due to property 3, we can say that u and v are functionally related. So I have already explained the meaning of functionally related. That means there must exist some sort of relationship or some sort of equation that connects the variables u and v. So see how we can get that relationship. So for this kind of relationship, you have again you have to investigate the given relationship here. So here we have two relations, u in terms of x and y and v in terms of x and y, and you want to have a relationship between u and v. That means you have to eliminate x and y from these two equations, and then definitely you will have a relationship. Why? Because this fact is ensured due to this fact. Because whenever the Jacobian comes out to be 0, that means u and v will be functionally related. Functionally related means there must exist a relationship between u and v. That means the variables x and y can be omitted from here, and we can get a relationship between u and v directly. So see, suppose I'm writing tan inverse x plus tan inverse y. Then from the knowledge of trigonometry, we know that the formula is for tan inverse x plus tan inverse y is in fact is equal to tan inverse x plus y 1 minus xy. This is you can see from trigonometry, this formula is there. Now we are given that tan inverse x plus tan inverse y, you are given that is equal to v, and this x plus y divided by 1 minus xy, this is in fact equal to u. So substitute the values here and you take tan inverse on this side, so you get tangent of v is equal to u. So means you have obtained the equation which connects the variables u and v. From here you can easily say that u depends on v, or from here you can say v depends on u. So such kind of situation is called A functional dependence. This kind of situation is called functional dependence of variables. So this was regarding property 3 of Jacobian. Now, next we can see the Jacobian of how to find the Jacobian of implicit functions. Suppose we have the variables x, y, u, v, and w, and they are connected by the implicit functions f1. Suppose the one function is f1 x, which is connecting the variables x, y, u, v, and second is f2 connecting x, y, u, v. And uv are implicit function of x and y. Implicit means you cannot obtain the value of x and y in terms of uv, or neither the value of uv in terms of xy explicitly. So there is this is a function, implicit function, and similarly this is also an implicit function. For that situation, I am directly writing the formula. The Jacobian is given by this formula: del uv divided by del xy is equal to minus 1 raised to power 2, because we are discussing the case of transformation of two variables to two variables. So del f1 f2 divided by del xy divided by del of f1 f2 divided by del uv. So using this formula you can find the Jacobian of such kind of implicit functions when the variables are connected by implicit functions. In general, because here we have considered the case of two variables. Now let us discuss the case of n variables. Suppose we have n variables x1, x2, xn, and they are connected with another set of variables u1, u2, and un implicitly by the function f1 x1, x2, xn, u1, u2 up to un equal to 0. The second function f2 like that, and so on. The nth function is like that. In that situation, the Jacobian in general is given by this equation: del of u1, u2, un divided by del of x1, x2, xn. So that gives you the value minus 1 raised to power n. So you keep in mind the power of minus 1 will be raised as much are the number of variables in the implicit function, because here transformation is from n variable to n variable. That is why minus 1 raised to power n, and here was the transformation from two variables to two variables. So here the power of minus 1 was 2. So this is the general formula from where we can find the Jacobian of implicit functions. So let us see one example regarding this type of situation. Example 4. Here we have a function, implicit function or relationship here, and this second one. So in fact this is case of two functions, so I can consider this as f1 x square plus y square u square minus v square, and the second one we call it as f2. Now we wanted to find here we want to find or prove that del uv over del xy is equal to x square minus y square divided by u square plus v square. So from the definition or the formula we have discussed, we have to find two things: that Jacobian of f1 f2 with respect to xy, then Jacobian of f1 f2 here with respect to the uv. So you can say the value of this is del f1 over del x, del f1 over del y, del f2 over del x, del f2 over del y. So from these relations you can obtain value of del f over del x is 2x, the value of del f1 over del y is equal to 2y. Similarly, del f2 over del x from here you can get is equal to y, and del f2 over del y is equal to x. After simplification we get this quantity. Similarly, we obtain del f1 f2 divided by del uv. So you can find these values from these two relations. You substitute the values here, and after simplification of this determinant we get value is equal to this. Now from the formula of the Jacobian of implicit functions, the del of uv divided by del of xy is equal to minus 1 raised to power 2, and here del of f1 f2 divided by del xy, then dividing the whole by del of f1 f2 divided by del uv. Substitute the value of this is equal to twice of x square minus y square, and value of this denominator part is twice of u square plus v square. So after simplification we get this answer. So here we have considered the case of implicit functions where the transformation was done from two variables to two variables. Then further we can see here the case of three variables ubw, xyz. The first implicit function, here you can consider it as second, and here we can consider it as third. Then we have to prove that the Jacobian of del uvw over del xyz, this is equal to this quantity. So we have to prove this relationship. So as mentioned here, we can consider this the whole relation as f1, this whole relation as f2, and this relation as f3. So this is f1, f2, and f3. So as done in the case of two variables, first we shall find del of f1, f2, f3 with respect to x, y, z. So you can see the value of this will be definitely, you can see the determinant here for this case will be del f1 by del x, del f1 by del y, del f1 by del z. Similarly, del f1 by del, sorry, here this is f2, del x, del f2 over del y, del f2 by del z. And for the third row, we can have del f3 del x, del f3 del y, del f3 del z. So from here you can see that del f1 by del x is equal to -1. So we have put here -1. Del f1 by del y, from here you can have, this is -2y, so -2y is there. Del f1 by del z is -2z, so -2z is there. In the same manner, from f2 you can find all these values, and from this f3 you can find all these values which are given over here, and the values comes out like this. So after simplifying this determinant, the value is this one. Again we find the value of del f1, f2, f3 with respect to del uv with respect to the variables uvw. So obviously in this case here, in place of x, y, and z, that in the determinant you will have u, v, w, and here u, v, w, u, v, w, and you calculate the values from the same functions f1, f2, and f3. For example, if you find del f1 by del u, so you will get 3u square, that is there. Similarly, del f1 by del v, so from here you get that is equal to 1, and del f1 by del w is 1 again. So in this way, in this determinant also you put the values and simplify this determinant, you get this expression. Now from the formula of implicit Jacobian of implicit functions, you can have the value of del uvw divided by del xyz is equal to -1 raised to power 3, and here del of f1, f2, f3 divided by del xyz divided by del of f1, f2, f3 divided by del uvw. So you substitute the values here in numerator and denominator, we get the desired result. So this was the case of transformation of three variables to three variables for implicit functions. Now we are giving here one exercise. Certain questions are there based on the three properties and this case of Jacobian of implicit functions. So 4 exercises are there. Then we have 3 exercises here. So in total 7 numerical problems are there. You solve these problems based on the discussion carried in this lecture. So that is it. We have taken these exercises and you know, the numerical examples so from the book H.K. Das Advanced Engineering Mathematics. This is the textbook, very good textbook here. So thank you. That's it.